we set up a race between the QPU, the quantum processing unit, and a whole bunch of state-of-the-art classical methods. And we found that for some of these simulations, the best classical approach would take almost 1 million years to solve the problems that we solved in just a few minutes.
Hello, and welcome back to Quantum Matters, where quantum computing gets real from D-Wave. I'm your host, Murray Thom. As we move past the hype and the theoretical to explore practical, real-world applications of quantum computing today and where the biggest opportunities lie in the future. Let's open the box and see what's possible. Today, we're going to talk about what it really means to go beyond classical, and specifically the groundbreaking peer-reviewed research published in the journal Science that demonstrated the first quantum computational advantage on a useful problem with relevance to materials discovery. Beyond classical, sometimes referred to by scientists as quantum supremacy or quantum advantage. We've seen demonstrations of quantum advantage before, but what's significant about this result is not just that it shows an advantage, it's that the advantage applies to a real-world problem. Now, we're going to discuss this result in the context of the broader field. And yes, we're going to dive into the technical details, but we'll start with the big picture, what this means for us, for our lives, and for this moment in history. And we'll do that before we go deeper into how it's done, what it takes, and the details of what was actually calculated. My guest today is a good friend of mine. We've been working together for over a decade, Dr. Andrew King, Senior Distinguished Scientist in R&D here at D-Wave, who led that groundbreaking research I mentioned off the top. Andrew, welcome to Quantum Matters.
Thanks, Murray. It's good to be here.
Just to begin with, I think probably the best place to start is for you to tell us a little bit about how you got started in quantum computing.
Well, I got started in quantum computing at D-Wave. So I don't have an academic background in quantum computing or quantum information theory or anything like that, or quantum physics. My background academically is as a graph theorist and doing algorithms and theoretical computer science. I was a postdoc and I saw the opportunity to come join D-Wave for working on a particular type of constraint satisfaction problem. And I took it. There was somebody I knew who worked here, and so I was very interested in the opportunity to come and work on constraint satisfaction problems in a practical setting. And so after I started working on that problem, I realized quite quickly that it wasn't a very good fit for the hardware. So I started asking, well, what makes things a good fit or not so great for the QPUs that we have? And following that thread of research has drawn me to, trying to mitigate these issues that might come up or trying to play to the strengths of the QPUs. And part of that led to quantum simulation. So what we have here is a programmable quantum material. And so we can use this to do quantum simulation in a very natural way.
Yeah, I think that's an interesting point because what you're describing, I think it helps people to see a window into our lives developing quantum computers, which is that we have an idea of the machine we're going to build when we set out. But quantum mechanics is also something that there's so much that we can still learn about. And so as we're going through developing and implementing the quantum processors themselves, we can measure them and deepen our own understanding of quantum mechanics and how we can use quantum mechanics in useful work. Now, one of the things I want to make sure we get to right at the beginning is the scientific result that I describe as the most exciting development in quantum computing in the last 2 years. So at a high level, can you tell us a little bit about the result that was achieved?
Sure. So we did a quantum simulation very fast. This quantum simulation was the simulation of the dynamics of programmable quantum magnets as they pass through a quantum phase transition. So basically, we set up a race between the QPU, the quantum processing unit, and a whole bunch of state-of-the-art classical methods that could potentially solve these problems. And we raced them, and the object of the game is to get equal or better solution quality to the QPU. And we found that for some of these simulations, the best classical approach would take almost 1 million years to solve the problems that we solved in just a few minutes using the QPU.
What a significant difference that is, right? Nearly 1 million years on the classical side, 20 minutes on the quantum computing side. I mean, what are the kind of, when we're talking about making a comparison like that, what are the classical resources that we're discussing that would take nearly 1,000,000 years to do these calculations?
Oh, well, it's not a laptop. It's the world's fastest supercomputer. And we can't do this calculation directly. We have to pretend that Oak Ridge National Lab is going to give us 100% access to their state-of-the-art supercomputer, which is obviously not going to happen. So we got a little bit of the supercomputer and then divided the number by the proportion that we had. So so GPU-based supercomputer, which was at the time the fastest in the world, the Frontier supercomputer, versus one little QPU.
And, I think in the domain of benchmarking, it's important to recognize that, we're talking about the very limits of computing, the absolute frontier of computing. So it's sort of like a demonstration that you do and you put it out there, and then everyone else who wants to try to do better tries to compete with that. How long has this basically been standing?
We demonstrated confidence in our result by posting the preprint on Archive when we submitted to the journal, and it can take 6 months to a year usually, if everything goes well, to get your paper published in a peer-reviewed journal at that level. And in this case, it took closer to a year, and the result still stands, and that was a year ago that it was published. Almost exactly, actually. People have been working at it, and there have been improvements in the classical methods that have solved some of the problems up to the same sizes that we had demonstrated with classical methods, but not to the size that we solved on the QPU. But what's really interesting to me is the fact that these are 3 different modalities that have demonstrated beyond classical computation. And they're all doing quantum computing. This is it's kind of mind-blowing that you can just do quantum computing with different devices of that kind.
Yeah, no, it's true. It's remarkable. I mean, the probably I think maybe the other thing is that, there is an interplay between classical computing and quantum computing. In order for us to be able to make computers of this level of complexity and sophistication, we have to use classical computers in order to be able to operate them. But then there's also this context of running applications where we're sharing work between classical computers and quantum computers. This result, I think, was significant because it was direct to the QPU, right? So rather than like a hybrid context. So I would say arguably the highest bar for a quantum computer to hit on its own. I mean, how would you kind of articulate the division of effort between a classical computer and a quantum computer in this context?
This is what I call a bare metal demonstration. So you don't do any classical post-processing or post-selection or anything like that. So when you're solving a problem for a customer, anything goes. It doesn't matter what compute resources you're using. What's important at the end of the day is the result that you get and the amount of money that you spend, basically. But when you're doing a scientific demonstration, there are certain kind of rules that you want to stick to. First of all, you don't want to do something that you say is quantum that is not actually quantum. And you don't want to be using classical resources in a way that significantly improves the appearance of the results from the QPU. So I find the bare metal demonstrations much more interesting because I'm really just kind of geeking out on these processors, and I'm really interested in seeing what they can do by themselves. So this would fall into that category.
Well, and I think how this speaks to people as well. I mean, sometimes I try to make an analogy to the Industrial Revolution, right? During periods of the Industrial Revolution, we have created engines that can basically do useful work for us, right? Like take an engine like a motor we would have in a car or something like that. That is an engine which takes fuel and it produces rotary motion with torque, right? At the time that engine might get developed, there might not be tons and tons of applications for rotary motion with torque, but because we can do it so effectively, right? The amount of RPMs that we can produce, the amount of torque that we can produce is so high relative to what we can do before, we can start to transduce that into other forms of work. So I think, to your point about this being like a bare metal QPU demonstration of advantage is that, now there's this opportunity for everyone approaching this field and entering this field to understand that capability and look at how they can leverage it for a variety of applications. And that's what's significant about this. This is application relevant, right? I mean, maybe, I'll jump to this point to what some of the applications are that this kind of work is relevant to.
Yeah. So, not everybody knows why you should be interested in solving the dynamics of a quantum phase transition. So a phase transition is like where you change a parameter of the system and you get a macroscopic reordering of the structure. The classic example is melting water. And in a quantum system, you don't have temperature because there's no coupling to the thermal bath in the systems that we're talking about. So you change a magnetic field instead. And so you go from a system that is totally disordered, in this case, to one that is, it's a different kind of disorder anyway. But what's important is that you're tuning a programmable magnetic material at the edge of one of its phases. And so a potential application is in the research cycle in materials design. So you have to design the material a priori, you have to fabricate it, you have to test it, figure out all these parameters, like where is the phase transition, for example. And then you need to send it back to the drawing board. You need to change some doping parameter, refabricate it. And so if we can shortcut that process, then this could be an enormous accelerant for scientific progress and materials production and research.
Yeah, I mean, that's a good point. I mean, if we think about it from the perspective of like, you were talking about like melting ice, or even going the other way, right? We start with water. It's a liquid. We can swim in it. There's a lot of disorder in that. Then the parameter that we adjust is temperature. And all of a sudden, the properties completely change at a transition point. It becomes solid. There's a longer range ordering, but it's not completely ordered like a crystal would be. And then you can skate on it, or you can now, move equipment across it or something like that. So, if we were going to like put this into the magnetic space, we use lots of magnetic parts. There are pieces that we use that snap into place, plugs and things like that, right? Whose properties are magnetic. And you can imagine a scenario where you would switch them to where the properties are non-magnetic. So sometimes they actually connect together and sometimes they release each other. So the most immediate application would be in, materials design, material simulation. I want to maybe push pause on the applications discussion to introduce a really important dimension of this calculation, which has to do with energy efficiency. So, we talked about the time it might take the world's largest supercomputer to do these calculations relative to the time on the quantum computer. What about from an energy consumption standpoint? What were those metrics like?
So obviously, if you're talking about a problem that's going to take frontier 900,000 years to solve or something like that, you have to think about the energy burn of that. And so some of these problems could take the entire worldwide electricity consumption for 1 year to solve. You can just say this is totally unreasonable in terms of both the amount of time and the energy draw that is required to solve the problem. So you got a huge advantage in energy efficiency. So one situation where you're trying to solve a lot of problems and you're trying to do it energy efficiently is Bitcoin or blockchain problems. So blockchain problems are predicated on the idea that you have a certain number of small computational problems to solve, and they have to be solved at a certain rate. And it should be profitable to mine the currency. If we're just talking about a cryptocurrency, proof of work cryptocurrency, it should be profitable to mine the cryptocurrency by solving these problems. So if you, instead of taking a classical hashing problem, you take a quantum simulation problem such as the one that we solved in this work, you can actually build a blockchain application around that. And so if you want to do that, you have to demonstrate a few things. You have to show that you can solve these problems consistently enough. And you have to be able to solve it across multiple QPUs. Otherwise, it's not going to be practical. So we actually wrote a paper on that, and it's been published on the archive and is soon to be published in a journal.
It's interesting because I had a conversation with someone about this point that, to do these calculations on a classical supercomputer might require as much electricity as the entire world uses every year. And their response to me was like, well, why do you even calculate it to that level of detail? You can just say it can't be done. That's so much electricity. That's never going to happen. But I think it's precisely to make the point that the quantum computer to do those calculations required less than $1 worth of electricity. And it helps maybe make more understandable the magnitude of the difference between classical computing and quantum computing.
You have to blow their hair back a little bit with these numbers.
Yeah.
I mean, there's a couple of reasons. First of all, if you're going to say something that is impossible, you need to quantify it in a scientific journal. That's one reason. And the way that you're going to justify this claim is by, looking at your extrapolation curve, which needs its own set of justifications. and say that you are here and this has a number and the number is 900,000 years.
Yeah.
Or something like that.
Well,
so yeah, obviously nobody would spend 900,000 years trying to solve one of these problems.
Well, and it's helping people to understand what this new thing is, right? I mean, and the changes go deeper than that at the like device level themselves. So for instance, like all of the computers and the chips that we're using in our phones and, like new chips from like Intel and NVIDIA, as those have been developing and have been doing more work, they've also been consuming more electricity. One of the interesting things about the quantum computers that we build here at D-Wave is they sit in refrigerators that cool them down to really low temperatures that are like more than 100 times colder than interstellar space. Just pause on that for a moment. So, in our daily lives, in our laptops, the operating temperature of our chips is room temperature. But when we turn them on, they heat up, right? Whereas in our quantum computers, the operating temperature is low temperature. But when we turn them on, they don't heat up. And that's the significant part, is that although the refrigeration system requires about 15,000 watts, what's arguably like, 60 to 100 times lower electricity consumption than common supercomputers that are measured in the megawatts category. The actual quantum computer chips themselves consume less than 1/millionth the power of like a mobile phone. And that means that as we go through these multiple generations of quantum computers being developed, the power consumption of the systems are flat because the chips themselves are not contributing like a noticeable amount of electricity consumption. So what's fascinating about that is the point that you're making. Blockchains for Bitcoin or other applications, that's a tool for allowing people to track a chain of events, like a ledger or a series of transactions. And that's something we can already do. It's just that when you look at what the quantum computer is, when you introduce that into that application, we estimate that can reduce the electricity consumption by 1,000 times. That's the part that's kind of new and novel that's getting introduced here by quantum computing.
And it's also, for better or worse, it's not just an energy consumption issue. It's an issue of being able to say the people who have access to these computers will be able to solve these problems and other people won't be able to.
Right. Yeah.
So you either restrict it or democratize it.
Now, the other thing is, that those are both applications of material simulation, blockchain. Those are both things where we've actually demonstrated how these calculations can be used in those applications. I think the other thing that's interesting is that in artificial intelligence, like in 2024, John Hopfield and Geoffrey Hinton won the Nobel Prize in Physics for Hopfield networks. These are a certain type of neural network where the neurons are kind of like affect each other bidirectionally. That was sort of the Hopfield network that John Hopfield proposed. And Geoffrey Hinton talked about like the energy-based response of that neural network. That's a useful tool for artificial intelligence. Well, that turns out to be exactly the machine instruction of the quantum computer, and it's kind of like a quantum mechanical version of that. Now, that's an application that's currently being explored. How much involvement have you had in some of those explorations and the connections there?
Not very deeply, I would say, but it's certainly a lot of AI practice is based on classical statistical mechanics, and similar to blockchain applications, is based on solving lots of not very hard problems classically. And so the question is there a way that you can use quantum computing or specifically quantum annealing to either accelerate these applications or get them done with less cost and less energy cost? And so we have some promising results, but you'll have to wait to find out more about that, I think.
Let's start to dive in a little bit more into this work here. We're talking about a demonstration of a calculation that a quantum computer can do that we don't think any classical computer could ever do in any reasonable period of time. No one would attempt it. What does it take to do a demonstration like that? Like how long, how many people did you involve, the organizations, how much classical computing time did you need? Can you tell us some of those?
It was about 1.5 years that we worked on this, from when we started even exploring the paper to having it submitted. And very, very early in that process, we figured out what we wanted to do, and we demonstrated that you could do it with a QPU. So that's not the hard part. The hard part is formalizing all the claims, figuring out what the classical methods are going to be, and doing the work for the classical algorithms, because you want to show that these problems are intractable. It's not a straightforward thing necessarily, and also it's not straightforward to do the classical calculations because they get so hard so fast, and it's not very convincing to fit a line on 2 data points. because who knows what this functional form is. So you need as much data from the classical computers as you possibly can get. And each time you add another data point, it like quadruples the amount of work that you have to do. And a lot of this work is just dealing with the classical supercomputer, doing the applications for the granted hours, and then dealing with the queue and all this stuff. So yeah, figuring out how to solve the problem with the QPU is easy. Figuring out how to optimize that is a little bit less straightforward. And doing the classical stuff is way harder than any of that. But maybe I'm speaking as somebody who spent a little bit too much time with the quantum computer.
Well, yeah, and I'd heard that, there was 11 organizations worldwide involved in this work,
Yeah.
And that, it took like over 100,000 hours of time on some of the world's largest supercomputers. I mean,
yeah, well, we certainly don't have all the expertise in house that you need. So you need somebody who really understands matrix product state algorithms well, really understands scaling of entanglement in these systems, PEPs, neural nets, et cetera, et cetera. So you need a broad base of expertise that we got from our suite of world-class global collaborators on this work.
Well, and I think, it just makes you appreciate, the level of effort and work that you put in, that those dozens of researchers across those 11 organizations, the effort that they put in. Because oftentimes, I think I run into folks who are kind of like, hey, why aren't there beyond classical demonstrations on every single application you would use a quantum computer for? And I think, we're trying to share a bit of an idea of like, it's a lot easier to do the calculations than it is to prove that nobody else could ever do them.
Yeah. And, if you do something before everybody else, it's a lot more difficult to convince people. And so the work is that much harder. So it's doing it first is the most difficult. But doing it at all is a huge amount of work. And so if you find that we can do things a little bit better, and we have found ways to improve the quantum methods since doing this work, we're not going to redo this whole exercise again just because we think we can add another zero to the advantage. You have to move on to other things. Well, maybe it's a privilege to be able to say, oh, we're just going to move on to more interesting things, because doing this beyond classical computing with quantum computers is boring now.
Well, I love that. Yeah, you heard it here first. I mean, the other aspect to it is that, the goal here is to do the calculations, demonstrate the work, and give folks confidence in it. Like they can actually go and explore it and attempt it. And part of laying those foundations wasn't just this single piece of work, right? There were like 5 papers written in Nature and Science portfolio journals leading up to this in order to construct the case in a body of work. And that's, I think oftentimes people feel like, oh, science is like when, someone crosses the tape at the finish line. It's like, well, this person was first. But, it's actually a much larger body of evidence. It's all the steps they laid to get up there. Everyone is kind of using all of those references to help understand it.
Yeah. So, a few years ago, there was no demonstration that we could do coherent quantum annealing even. And so that was the first step. And so coherent quantum annealing means that you don't have any thermal effects. And this is where you get really into the, not only the quantum effects that are interesting, but the quantum effects that are easy to understand and explain in an experimental context.
Right.
So if you mix up thermal and quantum effects, it becomes quite difficult. But that's great if that's what you want to do, because we can do that, but doing it one or the other is more difficult. So we did this in a very easy system to solve, a one-dimensional system. And then we moved on to optimization problems because, people were not totally convinced that experimentally you could see a quantum speed up in optimization. And so we demonstrated this in a Nature paper in 2023 using thousands of qubits in a 3-dimensional spin glass, which is what a physicist would say is like the most beautiful optimization problem. So we showed that you get a quantum speed up. So it's a polynomial speed up, which means that if you double the amount of time that you do with a quantum computer, it's gonna like quadruple the amount of time you have to spend solving this problem with a classical computer to get the same benefit. So basically that was a long-standing open problem, and we solved that. But even then, that was not the end of the story, because, like I said, like everybody knows you can't solve quantum simulation on thousands of qubits unless you're in some parametric limit. And so we had to demonstrate that we were not in that parametric limit.
Well,
and that was the hard part.
There are folks listening to you talk about like 1 dimensions and 3 dimensions. One of the things I want to sort of articulate is like, we're trying to describe the way the world is working, right? And when we use mathematics, we can make descriptions that are like incredibly detailed, So like if you think about like a string on like a violin that's vibrating, it's fixed at 2 ends. There is a lot of information we can describe about, at different notes, which parts of the string are moving up and down and which parts of the string are not moving up and down. So restricting ourselves to a one-dimensional system gives us, a simpler system on which to describe what's happening in a material. That you were doing that in a magnetic material. As you go from a bowstring to, let's say, like vibrations on the surface of like a drum head, which is in 2 dimensions. Now we've got a plane, not just a string, right? So those vibrations are kind of moving like the surface of the ocean, let's say. And then you imagine going to 3 dimensions. 3-dimensional vibrations would be like sonar, or clicks, where you're creating vibrations. Those vibrations move out in a 3-dimensional space, and then they might reflect back in a particular 3-dimensional structure. So that's the progression you're using as you're studying materials.
Yeah, all the foundation that you need is in the 1-dimensional system, so you have to start there.
So, there are, I've been talking about the structure of the calculations and what you're basing the calculations on, but there's also a degree of like refinement of control, of precision of the results and the measurements that you do, which when we do these in quantum mechanics studies, then translates into better operation of the quantum computer, which itself has positive implications for folks who are running applications on our quantum computer. So what kind of work did you do during the course of this project to refine the control and precision of the quantum computer?
What we were doing 5 or 10 years ago looks like child's play today compared to what we're doing. But I can talk about the refinement that goes into the calculations. So basically, when the system is calibrated, you get a one-size-fits-all calibration. And if you're asking a very specific question, then sometimes you can do a lot better than that. You can employ knowledge of symmetries in the system to refine the calibration. And by doing this, you can basically make the energy landscape you're trying to study more uniform. So there was a demonstration, the first demonstration that we did of a topological phase transition in an open quantum system in 2018 in Nature. And this was based on something called order by disorder. So basically you get an energy landscape that is perfectly flat. And when you add quantum fluctuations to that, a certain type of, it's like a harmonic basically that comes out of this. So you get structure by adding quantum fluctuations. And this only appears if your energy landscape that is supposed to be flat is actually flat. And when you're dealing with an 1800 qubit problem that you're kind of engineering for the first time, it's not straightforward at all to do this. So you need, exponentially many degenerate ground states to be degenerate, which means they have equal energy. So you basically need to do all this balancing so that you get this beautiful pattern of harmonics from the fluctuations. So what we do is we tune the heck out of it, basically, and it is very helpful for getting the most out of the processor.
Yeah, it's kind of like you're basically taking like a lake and then just quieting the surface of the lake so that if you're creating ripples, or let's say if there's like a little vortex in the lake, you can see all of those details. That's what you meant by topological, right? Is like the appearance of vortices and sinks, like holes in the surface.
Yeah, that is what I mean. But it's not exactly the flatness that you're talking about. It is more like seeing a standing wave in a pool.
Okay, perfect. So Andrew, I'm just loving the topic and diving into it with you. But we should talk a little bit about like what's next. What's on the horizon, for cutting edge quantum computing results in your mind?
We have our hands full. We are getting new controls every time we think we've done it all. They say, "Oh, here's another knob to turn," and we've shown some really exciting capabilities with some of these new knobs. So what we can do now is analog digital quantum computing. So basically, quantum annealing is based on a many-body quantum system that you guide from point A to point B. And sometimes you don't want to guide it, you just want to study it. You want to study its evolution, and you want to initialize an arbitrary state, and you want to read out in an arbitrary basis. So you can get much more information that way. And that's what we're able to do now. So using something called multicolor annealing, we, instead of bringing all the qubits along for the ride like this, we kind of play these weird games with them to do state preparation and readout. And we can do all sorts of really cool stuff in non-icing Hamiltonians. So it's really totally busting open the amount of systems that we can simulate.
Mm-hmm. Yeah, I mean, it's kind of like, it's actually kind of an important way to think about the different models of quantum computing, where like in quantum annealing, you're basically providing programmable quantum evolution, and you're kind of, I'm going to use a metaphor here, morphing this surface like a sheet and kind of like rolling a ball around in the sheet in order to get it in the direction you want to go. In gate model quantum computing, you're actually creating like programmable excitations. And to your point, like the degree to which you can apply controls and measure controllably in different dimensions gives you more information about the system. And what's happening here and what you're describing with the analog digital is that you're taking the ability to excite and measure in different dimensions and then bringing that into the context of the evolution part. So there's a little bit of a hybridization of the programming models here.
Yeah. We wouldn't want to say hybrid because that usually means classical quantum, but it's definitely an intermediate point between quantum annealing and gate model quantum computing, which it just really needs to be thought of as analog digital. And it's quantum annealing, yeah, it is like playing Marble Madness, except instead of moving the marble, you're moving the landscape.
Yeah, it's fascinating because, we're broadening the set of applications and our opportunity to demonstrate really large performance differences by being able to introduce these new controls. And that's information that we're sharing with, other researchers, other customers.
Yeah, I should make the point that none of these things are done using capabilities that are not available. So everything that we've done in all the papers is possible to do for our customers. And they're done on online systems. Back in the day, the systems were relatively noisy, and we had to say, okay, everybody don't use this system. I'm doing an important experiment on it, but we don't do that anymore. We don't even bother. Everybody's using it at the same time. And the throughput is kind of 10 QPU calls a second. So it could be 10,000 shots a second, 100,000 shots a second. People doing all sorts of different experiments.
And, as we're broadening that I think is a really key point about the significance to quantum computing, right? Is that we're expanding the capabilities of quantum computers. We're growing them in sort of new, fascinating, and unexpected ways. We're giving more controls over those systems. I mean, what do you feel this is doing to the sort of the distinction between what we would like to be able to do with quantum computers, what we can do?
Well, it's certainly blurring the lines because we can just do all sorts of non-icing simulations at this point. We've got too many things that we can do with these new capabilities and not enough time. So we are making the capabilities available to select research customers. And that's going to be very helpful for everybody, not just for them, but for us.
Fascinating.
So hopefully it's going to really accelerate progress.
Andrew, it's been absolutely fantastic having you on the podcast and getting a chance to talk to you about this result and kind of, pulling back the layers of the onion, allowing people to kind of see deeply into like the effort that went into it and the work that happens. So thanks very much for joining me on Quantum Matters today.
Thanks for having me. It's been a pleasure.
What a great conversation with Andrew. I really enjoy talking with him and exploring these subjects in quantum computing, everything from these dramatic demonstrations in terms of being able to show that calculations that would have taken the world's largest supercomputers nearly 1 million years being done on quantum computers in as little as 20 minutes, as well as, the ramifications from an energy consumption standpoint, like classical computers requiring nearly as much electricity as the entire world uses every year to down to less than $1 worth of electricity on the quantum computer. So that's going to be it for this episode of Quantum Matters. Thanks to you, our viewers and listeners, for joining me. Please follow so you don't miss an episode. And to learn more about how D-Wave works with organizations to get started and succeed with quantum, visit dwavequantum.com. Until next time, I'm Murray Thom. Stay curious about your quantum reality.